Now coming to the experimental setup, which is very essential to take it forward for experimentation. So we have this is the experimental setup in our laboratory, and this is the interface. Like it is meant, the two-fingered exoskeleton is meant to have a total of 7 degrees of freedom, 3 degrees of freedom for the index finger exoskeleton and 4 for the thumb exoskeleton. So these are the joint ranges for the index finger and thumb exoskeleton. You can see it is only 35 degree. It doesn't mean that it will move only the 35 degrees of motion for the human finger. This is the mechanism input angle, that is the crank angle of the 4-bar mechanism, because the crank angle is the one that receives the actuation by the motoring system. Like the motor is attached to the crank, which is provided to move 35 degree, and it will move the finger phalanges in a higher range, close to 60 degrees. And this is the exploitation, which involves the DAC card, like data acquisition based on NI DAC card. There is also another system which we have for the next system, that is Quansar based USB DAC card, data acquisition card. And we could be able to receive the sensory signal as well as the actuator input we can give by bidirectional channeling by this two DAC cards, one for the index finger and another one is for the middle finger, and we could another one is for the thumb, and we could be able to do the graphical simulation along with the experimentation by the LabVIEW platform. And here is the mechanical realization, because this is asked by the reviewers in order to make sure that how it is getting fixed to the finger joints and where the motors are placed and how the motors are placed. And this is basically the mechanical realization, because just by simulation alone is not enough for the practical application. So it must be implemented, tested, at least pilot testing in the experimentation, and must be realized mechanically as well. And so this is the mechanical realization where the motors are placed with the screws, and we could see clearly that the 4-bar mechanism where this is the fixed link or the ground link, and the motor shaft is attached to the crank, and the floater or coupler is attached to the finger phalange or phalanges. And we have another link, which is the rocker, so that obeys the crank movement. The crank is the input link, which is moved by the motor actuation. So this system, what I wish to show here is the system will not be moved by the master. Where is the master? The human finger is generally the master, but this is basically a master-slave system in which the finger basically becomes the slave, where the master is the exoskeleton device. So the slave, which is the finger, human finger, could not be able to move this exoskeleton because it is fixed with the motors, so that this exoskeleton will bend the finger by the actuation that it receives from the motors. That's all. So a human being, after wearing this exoskeleton, he will not behave like a master. Rather, he behaves like a slave, where the master is the exoskeleton. So this purpose of the exoskeleton is to behave as a physiotherapist. And coming to the redundancy resolution. So first of all, let me quickly, you all much familiar with the term redundancy. Redundancy means excessiveness. Some of you would have come across the NPTEL lecture of mine, where there is separately 30 minutes lectures, like 1 hour lecture is meant for redundancy resolution. So interested candidates can go through those lectures also. So redundancy means excessiveness. For example, a system has 4 degrees of freedom. A robotic system has 4 degrees of freedom, but it is meant to move in the planar motion like this, for example. So you can see this system is meant to move in this fashion. Where it is moving in a plane, whereas the system has 3 degrees of freedom here. So one, this is basically the round one is the placement for the motors, attachment for the motors. This is meant for attachment of the motors. And you can see there is a meaning here. You can see 2 markers, which when you connect it, it becomes a line. So when you start, you have this fashion, and in the end, it behaves like this. So from the base to the tip, we could be able to get by vector computation, we could we could get the desired or the experimental or the human desired joint angle in order to make the system to follow this angle. That is the ultimate aim of this redundancy resolution purpose. So again, I tell redundancy resolution is nothing but you have excessive degrees of freedom of the robotic system in order to make the system to perform a task in the Cartesian space, right? So degrees of freedom, when I talk about it, there are two spaces coming into picture. What is that? One is the joint space or the robotic system space. Another one is the Cartesian space. So if the degrees of freedom of the robotic system is greater than the degrees of freedom of the Cartesian space, then the system is redundant system. So it has 1 degrees of freedom. For example, here in this case, the robotic system has 3 degrees of freedom. You all know the robotic systems degrees of freedom means number of joints. Number of joints means the number of actuators involved. So there are 3 joints here. So 3 degrees of freedom for this robotic system meant to move only in the planar Cartesian space, X and Y. So it has 1 degrees of freedom extra as compared to that of the Cartesian space. So it's a redundant system. So what is happening here is the purpose of this study to resolve the redundancy in this planar movement is given this type of desired angle, you fix the motor, and by the control action or by redundancy resolving technique, you solve it to follow this trajectory. Where is the trajectory I'm giving again? Let me explain it very clearly, because this is explained in our IEEE transaction manuscript. So it is basically the desired joint angle of this 4 bar, second 4 bar, and the third 4 bar, which is obtained from this vision system placed over the top of this planar surface. So when it is moving like this, when it is moving close and follow a straight line. So this is where the redundancy task is. Grasp it and translate the object in this straight line fashion. So in this entire movement of this mechanism, where the finger is, the human finger is the master here, and the robotic system is a slave here. Why? Because there is no actuators attached here. So this is the primitive setup that we have taken in order to get the desired joint angle for the redundancy resolution. So the joint angles are computed in such a way that experimental angle computation, which is nothing but getting the vector computation based angles between the initial vector and the instantaneously varying vector, v1, v2, and the cosine of it. Then comes to the task decomposition, which is a very important technique proposed by Sunio Yoshikawa in the year 1991. So Sunio Yoshikawa proposed redundancy resolution by task decomposition in such a way that you all know that inverse kinematic relationship, which is nothing but given the desired position and orientation of the end effector, you need to find the joint angles. And that is started from this power kinematic equation, where the power kinematic equation is definitely having only one solution. That is, given theta, input as theta, joint angle, obtain the tip position or the end effector position. So whatever you feed, you will get only one solution. That is not the case for the inverse kinematics, where the inverse kinematics has the problems of having so many solutions problem, or no solution problem also. So which one to select? If it is more solution, how do you select the optimal solution? So here is the thing, like you all know that the power kinematics expression is given by x equal to f of theta, and the differential kinematics is related by x dot equal to j into theta dot. That is obtained, all of you know that it is obtained, this differential kinematics equation is obtained by Taylor series expansion of this first equation, which is the power kinematics. Taylor series expansion and ignoring the higher differential terms. So the solution to this differential kinematic equation is theta dot equal to j pseudo inverse xd dot plus the redundancy term I minus j pseudo inverse j into some vector, which is given by this expression k which is a constant, into the partial derivative of a performance criterion. The performance criterion could be joint limit variation or the manipulability measure. Manipulability measure is how far your robotic system is from the singular configuration. So that is the measure, that is the performance criterion we have considered in our study in resolving the redundancy. So what is the solution for inverse kinematics? It is term 1 and term 2, where term 1 is primary subtask, term 2 is secondary subtask. Primary subtask, primary subtask is nothing but given the desired trajectory, follow the trajectory. That is what this primary subtask is. Secondary subtask is involve the redundancy or utilize the redundancy or take advantage of the redundancy in order to do a secondary subtask. What is a secondary subtask? Avoid obstacles, avoid singular configurations, or avoid joint limit violations. So these would be the additional work or the secondary subtask that we take in advantage because of the redundancy involved in the system. So this is the vector, which is the symbol O, is meant for taking advantage of the redundancy. So here we have taken that expression for O is a constant multiplied by the partial derivative or the first derivative of your criterion. So I have considered the criterion being m of theta being the manipulability measure, which is given by this expression root of determinant J transpose. You all know what is J. J means the Jacobian matrix. So when I say Jacobian matrix, some of you will get the idea. So Jacobian matrix is nothing but the partial derivative of your expression, that is power kinematics with respect to the joint angles. And let me put forward one important point before I get into this task decomposition, which is we consider the Jacobian matrix, which is JP, because Jacobian matrix can be decomposed further into JP, JO. What is JP? Meant for positioning or the linear velocity of the end effector. JO is the Jacobian portion meant for the orientation or the angular velocity of your end effector. You all know that. What is Jacobian matrix? It is the linear. It is a linear mapping that helps to map your end effector velocity to the joint angular velocity. You know that end effector velocity is further divided into two portions: linear velocity of the end effector and the angular velocity of the end effector. So this x dot is nothing but a column vector having two elements v and omega, which is equal to j into theta I dot, where j is further given by the column vector of two elements jp, jo. Okay, so here in this task decomposition proposed by Sunio Ishikawa, it is basically under the condition that J is the one which is not having the orientation term. JO is not there. We do have considering only the tip position of the end effector alone, not the orientation. Okay, so that is the assumption that this study involves. Very important point it is. If you are not considering about the orientation portion of the Jacobian matrix. All right, so coming to this part, we are maximizing this Jacobian, this manipulability measure. What is manipulability measure? That it gives how far you are from singular configuration. You all know the singular configuration is nothing but a lock configuration. It means that it locks the system where the system is having higher velocity of the joints, so that the system is locked. It will not move. Whatever joint angular, whatever being the actuation by the joint, which is nothing but the motor. Whatever actuation is given to the motor, it will not make the link to bend, the joint to move. And that leads to higher, very higher joint angular velocity. So singular configuration is the configuration that is not a favorable one, must be avoided. So your manipulability measure must be maximized. It means that you are coming very away from the singular configuration. So there is something proposed by Sunio Shikawa that this Kp is a constant, where I have taken this Kp being a variable in such a way that how it is getting varied by a cubic polynomial with respect to time, which is given by Kp of t equal to Kp0 plus Kp1 of t plus Kp2 into t square plus Kp3 into t cube. It's a cubic polynomial. You can go for quintic polynomial also to compare this. That could be a quick research progress, that which gives you the better one, whether it is quintic or the fundamental cubic polynomial based. That could also be a research quick work. And then the concept is to have the discrepancy being minimized. That is, the root mean square error is to have the discrepancy or the difference between this joint angle by the inverse kinematics and the experimentation angle. So these two difference between these two angles, experimental angle and the inverse kinematics based redundancy resolved angle, how it is getting minimized. So that is getting minimized by providing the optimal redundancy parameter. So that is the task. Like we are getting a best Kp, that is optimal Kp, in such a way that this root mean square error is minimized. So that is the thing. And we have obtained the results in such a way that the thick lines or the experimental joint angles for the for the exoskeleton, that is for the index finger exoskeleton, you all know that the 3 degrees of freedom. So you can see that is having the variation, and you can see that it's highly minimized with less than 1 degrees being the root mean square error, and we have the tip getting precisely matched, and we have the redundancy parameter. You can see there is something called redundancy parameter which is varying with respect to time. I just normalized the time and to show the uniformity among the results. You can see the redundancy parameter getting varied in such a way that it varies in magnitude as well as in sign. So this is the thing, it varies in magnitude as well as in sign, and you can see an increase in the manipulability measure by this method, because we are instantaneously maximizing the or optimizing the manipulability measure, which is a performance criterion here. And this is the same results for the thumb. You can see the thumb exoskeleton, which is also having the joint angle variation, but you can see precisely there is a discrepancy in the end of this time, which is basically it is coming out to be 7.65 degrees being the root mean square error. And you can see the variation of the Kp as well as the manipulability measure. And this is the experimentation that shows the translation, that is the straight line movement of the index finger and the thumb exoskeleton. So you can see this also, the translation motion, that is because as I mentioned you earlier that the motors are basically moving the system in such a way that when the motor attached system is owned by the human being, the system is the master and the human being is the slave, because he cannot bend the exoskeleton. So the master here is the exoskeleton and the slave is the human finger. And this is basically the slender object translation movement performed with the combined exoskeleton in translating the slender object or a fine object, a coin, the performance. And here comes the force analysis, because we are not satisfied only with the precise movement, human-like movement by the exoskeleton. We must utilize the movement in order to have the grasping task. So once you grasp, you are in contact with the environment. So we have performed a grasping task in such a way that we have considered the system with ideal dynamics. It means that it has only the unity friction term. The rest all mass is 0 and the rest portion is 0. So tau equal to 1 into theta dot. So or q dot. So here Q is the generalized coordinate of the robotic system. Instead of theta, let me precisely say Q. Q is the generalized coordinate. It could be the revolute joint variable theta or the prismatic joint variable d. So the concept here, in order to have the force analysis, is to consider the system being ideally dynamic system. It means that tau equal to q dot. So with that concept, we have performed the control by giving the desired trajectory of the force to grasping part, where the force sensor is in the contact between the human finger and the point of contact of the object to be grasped. So we have grasped a deformable object so that we could get the precise trajectory, actual trajectory of the system. So here is this trajectory matching that is obtained by the system. So this is basically considering the environment as a spring, so that K into X minus XE is the spring force that is obtained from the environment. It means that X is the actual trajectory of the system that is obtained from the forward kinematics, and X init is the initial position of the fingertip. So that is the concept to perform this task, and we have performed this with the similar finger-sized human subjects, 5 subjects, and this is the statistical result analysis with the simplest one. We did not take it forward to involve analysis of variance, like we stopped within the 5 subjects with simple mean and standard deviation. And here comes, that is something much taking to the higher level of controlling the system, the exoskeleton, with your subjects, human subjects' intention. Like for example, human subjects thinking, like by EEG. It has been done in my PhD. That with the same concept, like the human subject is having his forearm healthy and his hand part is not functioning. Its hand part is impaired, whereas the forearm of the human subject is working. So we have done utilizing the muscle signal, EMG signal, in order to provide the grasping. And recently in 2019, it has been done with the same task of finger motion involving the brain signal. Like we considered the entire arm is not functioning, impaired. So in that way, only the brain is functioning. So we could able to control the system by utilizing the brain signal. And you can see this is the task. What is the task for this is basically we have made the graph on our desktop in our laboratory in such a way that it has to have this movement. Like this is the extension and here is the flexion. And intermediate, we do have like 10 degrees or 5 degrees joint variation to have the input and output pattern generated for utilizing the ANN, like artificial neural network. It is coming under the supervised mode. Supervised mode will be having both the input and output pattern. We have the teacher there. Like for example, given this input, this is the output. Given that input, that is the desired output. So we do have the desired inputs and outputs. So it is coming under the supervised way of learning the neural network. So we have utilized a multi-layer network with a single hidden layer with 30 hidden neurons, and where the input is the heart parameters, activity, mobility, and complexity of the biosignal, and the output is the joint angle, which is nothing but the metacarpophalangeal MCP joint angle corresponding to the movements, flexion and the extension movements. So input is there, output is there. So what is this angle indicates the output. How do we calculate the input? That is basically obtained by LabVIEW platform, the online signals that has been filtered and obtained to follow, like to compute the heart parameters. So we have the joint angles. For example, you keep here and we know which angle it is. It is 60 degrees. So it is 90 degrees. So it is 0 degrees. So by these lines, we know what is that output That's the desired output. And the corresponding input is obtained from the computer by this computation in the LabVIEW programming part. So this is the testing, that is the BioPack, which has 8 channels. And this has been interfaced through DAC, and we do always follow the LabVIEW based programming part. And here is the demo of this system, of this experimentation. Here is the subject, and here is the exoskeleton. We do have with the LabVIEW based system interfacing with NI DAC and LabVIEW based control code, or the intelligent mapping, you can say. The graphical interface is to show how this joint angles are getting mapped. The desired joint angle, bending, and extension, flexion, extension. So that is what getting done here. He flexes accordingly, this also flexes. He extends, and this also getting extended. So that graphical representation is shown here in the graphical simulation platform, which is the LabVIEW. And here comes something beyond what we have seen in the supervised mode. You may be knowing that many of you are working in AN, and also that supervised mode and unsupervised mode are the fundamental learning techniques in ANN. So supervised based learning technique we have seen for classification purpose. It classifies. When I flex it, I get corresponding parameters and where it is. It is for this angle or that angle. So it is classification. And here comes something called a regression problem. So regression problem. So we do have the continuous values, how we do this mapping. So this is nothing but the inverse kinematics. So here we are trying to perform inverse kinematic control of the index finger exoskeleton, which is coming under the regression problem in ANN, artificial neural network. So you know that the forward kinematic data can be utilized in the supervised mode. For example, I am generating the data input-output pattern such a way that I do not know the inverse kinematic angle. So the inverse kinematic solution is nothing but the joint angle. Getting the joint angle is meant or taking us towards the control of it. So what happens here is, by forward kinematics, we could able to feed the joint angle and get the tip position. So we can do some lakhs of input and output data ready. Then we can do it in an inverse map based. For example, inverse map based means we are going to perform inverse kinematic control. So inverse kinematics we are going to do. First of all, in supervised mode, we need the data. Data generation is the first step in supervised mode. So we are generating the data in such a way that we provide the joint angle, and from the forward kinematics, they're getting the corresponding tip position. So input is joint angle, output is tip position. So 1 lakh or 10 lakhs of input and output are there. Now we inverse it. So we take a neural network, say a MLP with 2 layers, that is hidden and output layer only, and then we feed it in a reverse manner, in an inverse map, in such a way that we give the tip position as input, and we are trying to get the corresponding joint angles as the output. So what happens there is, if the system is redundant, that means excessive joint angles, so the system gets confused. So because there is one-to-many relationship exists. So that way of doing the reverse inverse map from the data generated by forward kinematics will be working provided the system is non-redundant. If the system is redundant, then it is not possible to go by the supervised way. So alternative way is to go by unsupervised mode. What is unsupervised mode? You have the input, but you do not know the desired output of it. So that is called unsupervised mode. So it is tougher, but it is quite interesting, so that we will be resolving the redundancy in a precise manner as compared to that of the supervised mode. Because supervised mode for the redundant robotic system, it fails, whereas the unsupervised mode for redundant system, it gives us the very good solution. Okay, so how we are going to do in this is by actuating, like the inverse kinematic relationship is learned directly by unsupervised mode by actuating the robot with the joint angle configuration generated by the neural network, then adapting the network for the positions reached by the end effect. All right, so what happens here is by the given desired input where the robotic system has to reach, the network, which is unsupervised neural network, will give you some angle. So that some angle, you will take it and feed it to the forward kinematics, you will get one desired, so you will get one actual position. I need to go XD, whereas my neural network will give X0 or theta 0. So theta 0, I feed it to forward kinematics, so I get X0. Instead of going XD, I have reached X0. Then from X0, I move to X1 by getting the joint angle theta 1 from the network. So what happens for a given XD, I have now two patterns ready. What are those patterns? X0, theta 0, X1, theta 1. So I'm training myself with these four values or the two patterns set. X0, theta 0, X1, theta 1. Right? So this way is the method or approach in unsupervised mode of performing the inverse kinematic control. So this is done by coherence self-organizing based inverse kinematics mapping based technique. So first of all, we need to start with the coherent self-organizing map K-SOM architecture, which is nothing but a lattice. It can be 3D or 2D lattice. All right, so lattice is nothing but the arrangement of the neurons. Each black dot is the neuron. Each node is the neuron here. So this is arranged in the 3D form. Okay, so the case of lattice discretizes. What it does is you have each neuron, and each neuron is associated with an input space and the output space and a linear map. So my friends, let me tell you, given the input, say X in the Cartesian space, precisely it is XD from the input space. So we need to have the output. So the output is nothing but the joint space. How do you know the output? How do you know the input space? Because I am the one who is providing this architecture with the ranges of input and output. So ranges of the input, say X equal to -1 to 1, Y equal to 1 to 3, Z equal to -5 to 5. So I provide the range. So range is provided, so it is a cuboid. And likewise, it is a joint angle, which is also having a range, like theta 1, theta 2, theta 3, or having the ranges 1 to 20 degree, -50 to +50 degree. So that's the range. What it does is the K-SOM lattice, it discretizes the input space to the number. How many number it will discretize? It will discretize the input space, which is equal to the discretization of the output space. That means it discretizes the input and output to a finite number of cells, which is equal to number of neurons present in the lattice. Then, and each neuron, as I mentioned you earlier, it is associated with a weight vector, which is having the same dimension as the input vector, and a linear map, and the corresponding joint angle. Okay, So this is Wi. For example, ith neuron has the three parameters such a way. It has Wi, weight vector Wi, output theta I, and mapping, which is AI. That maps from the given input to the output. All right. That means given X, find the corresponding output theta. So you all know what is generally when we do with the robotics, it is forward kinematics where X equal to f of theta. So what is the input? Theta is the input. And what is the output? X is the output. Whereas in terms of inverse kinematics, what is the input? X is the input and theta is the output. So theta equal to G of X. So that G is the mapping. That is nothing but Jacobian inverse. All right, so that is the one obtained by the linear map A. So each neuron is associated with these three parameters. So a joint angle is learned to reach near the local zone, and a linear map is learned from accurate positioning within new zone. And here is the robotic system. Here is, let us take only the index finger exoskeleton. The case-based learning is shown here. First is given the desired position, compute the winner neuron. This is a neuronal lattice. So we are finding the desired trajectory. The desired XD is given by this square. And let this guy be the green dot being the winner neuron. So that is obtained by the computation of the Euclidean distance between the neuronal position as well as the given desired position, XD. And then once the desired position is given and the winner neuron is found, there is something called coarse movement. That means a rough movement towards the target or the desired position, XD. So that is given by theta 0 out equal to S inverse into summation of this, which is obtained by the linear mapping. Okay, that is nothing but this what you have obtained, theta equal to G of X. From that, we could be able to get this force movement, which is X naught, which is obtained by providing this output from the network to the forward kinematics equation, gives you X naught. So that means it was here. Then, having computed the winner neuron, you are now finding the force movement, which is X naught, obtained from the network output theta naught, which is given by S inverse summation of this to this. This is the network performance, like overall response of the complete neurons. So this is the one. This is the output theta naught. I feed this theta naught to the power kinematic equation because you will be definitely having the power kinematic equation. So from that, we get X naught. Then from coarse movement, we are moving to fine motion. That means fine motion is, here is the coarse movement and fine movement is much closer to the desired position. And this fine movement is obtained by having the discrepancy, that is XD, X naught. Whereas your force movement is obtained having, yes. Prajapati. Yes, can I continue? Professor Amit, am I audible? Professor Amit?
You are audible.
Yes, please. Can I continue?
Yes, sir. Yes, sir.
Okay, fine. Thank you. Yes. All right. So you know that this force movement is obtained by considering the X desired and the neuronal's weight. Okay, or the winner neuron's weight, corresponding weight. These two parameters are considered in order to obtain the force movement's joint angle. And after reaching the coarse movement, we are getting closer to the desired position XD. by an amount x1 that is obtained from theta 1, which is given by theta naught plus summation of this, where we consider the discrepancy, which is the error, which is xd and x naught. With this discrepancy, we could go much closer to the desired position. So this is called fine movement. So given a desired input, these are the 4 steps involved: finding the winner, force movement, and then fine movement. All right, and then by repeated movement, fine movements resulting in accurate positioning. So till this is nothing but the training phase, the learning phase. That means given input, new input, we do find the winner and then coarse movement, then fine movement. Then give one more input. This is say XD is here. Then this guy becomes the winner, and then again coarse movement, fine movement. Then like this, when you do for say 5,000 to 10,000 desired positions, XD, new XD, in the end of the 5,000 iterations, say 4,995, you can say that this fine movement reaches the x1 is equal to xd with a small tolerance value to be accepted by you. Right? So this is the training, and the testing is done by repeated, given the desired only once coarse movement and then repeated fine movement will make your testing successful. All right, so this is it. By repeated fine movement in reach results in accurate results. And this testing, as I mentioned you, it can be done for several trajectories. It can be a straight line, it can be a circular trajectory, whereas you have to do the training with random points covering your work volume or the workspace of the robotic system. This should go back. Right, so here is the results. This is the work volume, and here is the neurons settling down in covering the work volume and the work volume of the Cartesian space and the joint space. These are the 100 neurons or 1,000 neurons getting settled here, are sparsely covering the work volume, the input space and the output space. Nothing but the discretization of your input space and the output space. And we have performed a straight line trajectory. This is simulation is shown here. There's a given in the straight line, and this is the output that is obtained from this inverse kinematic based control of it. And here is the exploitation demo, which is meant to follow the straight line, and it's the one that makes the finger to follow the master. And here comes something interesting part, as you have seen so far, because now we are entering into a new exoskeleton design, so that it is meant mainly for grasping task, because here in this exoskeleton, where it is placed on the lateral surface of your fingers. So lateral surface of your fingers placement will be providing you lesser normal force as it is placed on the dorsal side. You can see when the robotic system or the hand exoskeleton is placed on this dorsal side, it will make the fingers bend to provide very good normal force as compared to the placement on the lateral surface. Okay, so here the system is placed on the lateral surface. So we have designed a new exoskeleton which is not direct driven, because here you can see it is a direct driven system, which means that how many number of joints, accordingly number of actuators are placed for the robotic system. But what is the disadvantage of this way of utilizing the direct drive mechanism? the very important aspect here is the control becomes tedious because you have several degrees of freedom. Several degrees of freedom means several joints. Each joint is actuated by a motor. So you need to control each joint by controlling the motor. So control becomes tedious and the system becomes heavier, bulkier. And the volume also becomes, it's not compact, it is quite bigger in size and heavy in weight also, and highly computational towards control problem. So we have gone to the development of new exoskeleton meant for grasping purpose, merely grasping purpose. And the concept is coming under the title Development and Robust Control of a Hand Exoskeleton with the Force Feedback for Grasping Assistance. All right, so here comes the salient features. The salient features of this exoskeleton is or nothing but grasping task meant for grasping. It is compact because we are trying to involve one motor for each finger. How many degrees of freedom each finger has? Anybody? Each human finger has how many degrees of freedom? Each
3, sir.
3. Somebody? When Saraswati, 3. Somebody? Because you cannot say all the 5 fingers. It is basically 4 fingers and 1 digit. 4 fingers and 1 thumb, isn't it? So collectively we can say 10 digits. D-I-G-I-T, digit. Okay, so 4 fingers in one hand, we do have 4 fingers and 1 thumb. Collectively 5 digits. So let me tell you, the index finger and the other 4 fingers, you can say the 4 fingers totally they have 16 degrees of freedom and the thumb has 5 degrees of freedom. So the human fingers for one hand is basically 21 degrees of freedom. I'm excluding the wrist degrees of freedom because the wrist degrees of freedom are given to the arm, because the human arm has how many degrees of freedom? It has 7 degrees of freedom. 3 in the shoulder, 2 in the elbow joint, and 2 in the wrist joint. So totally 3 plus 2 plus 2, 7 degrees of freedom for the human arm. Whereas for the human hand, the say right hand, it has how many degrees of freedom? 21 degrees of freedom. The thumb alone has 5 degrees of freedom. The index finger and the other 3 fingers also have 4 degrees of freedom each. The MCP joint has, the MCP joint is nothing but this joint. This joint has 2 degrees of freedom. This has 1 degree of freedom. This has 1 degree of freedom. So totally 2 plus 1 plus 1, 4 degrees of freedom. For one finger, it is 4 degrees of freedom. Okay, somebody is saying may vary also. That is true, but precisely we can get set with 7 degrees of freedom, and hence the human arm is basically a highly versatile robotic system. All right, so for say for a single finger, it is 4 degrees of freedom, but what is here seen, it is 1 degrees of freedom. That means we are going to move this entire finger with only 1 motor by a robotic system. So that's why it is called under actuated system. And because of this under actuation, the system becomes lightweight and the system is adjustable to various finger sizes. Elderly human subjects generally have a thicker finger size and also lengthier one. So it can be adjustable to various sizes. It's one of the good salient features and easy to wear. The system is easier to wear as compared to this system. And sufficient force transmission to the fingers. That means being placed in the dorsal surface, it could be able to provide normal force, which are quite sufficient for the system to bend the fingers in order to provide normal force to the object to be grasped. And here is the kinematic modeling of the two-fingered hand exoskeleton. And you can see this is the CAD model developed in such a way that one linear actuator is meant for a digit. It's a human digit. And this is the mechanism, hand exoskeleton mechanism. On the hand exoskeleton mechanism, the zoomed picture shows 3 holes here, which is adjustable one to be screwed up. So that 1, 2, 3 is meant for different sizes of the finger lengths. Accordingly, these screws also to accompany various finger sizes. Then this figure on the right hand side, which is meant to develop the kinematic model of the system. The kinematic model is based on closed loop kinematic modeling, because so far in the serial link and all what we have studied is open chain kinematics. Here it is closed loop kinematics, closed chain kinematics. All right, by this closed chain kinematics, which involves portion of this looping is covered or is closed by the finger links. There are 2 loops here, and the finger links are helpful in covering the or closing the loop. And by a tedious computation of the kinematic modeling, we could show here only the tip positions of the finger that is obtained from the exoskeleton kinematic modeling. So X tip, Y tip are basically this tip of the finger exoskeleton of the finger, human finger, wearing this exoskeleton. Okay, so this is the X tip, Y tip of the index finger exoskeleton is shown here, and which is having L3 cos theta 3 on the E. These parameters are mentioned here when you see the slides. And then comes the kinematic model validation. You can see that this has been tested in order to have this trajectory coming out. Given this angle that is moved by this actuator, what is happening here is this trajectory that is coming out, and this is the trajectory that is obtained by tracing this fingertip. When we trace this fingertip by a vision system, we could say that how this tip trajectory has been tracked by this system. And here is the real system motion. This is how it is meant for moving this. The smooth movement is provided by this linear actuator thanks to it. And here is this trajectory getting traced successfully, so that the system is getting, the kinematic model is validated, so that it is not having discrepancy with the real fingertip trajectory. And here comes the force modeling. After calculating the tip position of the finger using kinematic model, differential kinematics allows to develop direct relationship between the Cartesian velocity theta 3 dot and the Jacobian through the Jacobian. Okay, so x dot equal to j theta 3 dot, and the relationship between the joint torque and the actual fingertip position is given by the static relationship, which is tau equal to j transpose into fingertip f, fingertip force, where from which f can be the j transpose inverse into tau. To calculate the actual force of the fingertip, we have considered again the ideal dynamics, which is nothing but zero mass and unity viscous friction has been considered. Hence, the joint torque with this ideal dynamics approach gives you the dynamic model tau equal to 1 into theta dot. Thus, the actual force at the fingertip is given by F equal to G transpose inverse into theta 3 dot. Yes? Can I continue? To submit. All right. Then comes the relationship between the control input and the velocity of the linear actuator is given by d dot equal to a minus bu. And this is obtained where a and b are obtained from the data sheet of this actuator. From the kinematic model of the proposed exoskeleton, the relationship between the joint variable theta 3, which is nothing but the active angle of the exoskeleton, and the actuator displacement d can be written by this expression, which is theta 3 equal to cos inverse L2e square plus L2 square minus of d plus L1 square divided by this plus tan inverse of this x by y, which is equal to f of d. The actual force F act is equal to J transpose inverse into theta 3 dot, and FA is obtained by the norm of it, where psi is the one involved in this expression, which is given by J transpose inverse now. And the error can be considered as the discrepancy between the desired force and the actual fingertip force. And the error velocity is given by the derivative of it. And now coming to the sliding variable computation. In order to perform the sliding mode control, we need to first describe the sliding surface by the first order equation, which is S equal to E dot plus lambda E. When S equal to 0, E of t is given by this expression, E of 0, initial value of the error, into E power minus lambda t. Sliding variable dynamics can be written as S dot equal to dou S by dou d into t dot. And S dot is given by this expression, which is having the U term, which is controller term, where A1, A2 are given by this big expression. And now coming to the stability analysis in such a way that quadratic Lyapunov function is considered as the candidate, which is given by V equal to half into S square, where S is sliding variable. The time derivative of this Lyapunov candidate is given by V dot equal to S into S dot, where V dot is substituting the S from here and the S dot. So we get control law being U equal to 1 by V1 into A1 minus rho signum of S, which will make the time derivative of the Lyapunov candidate being less than equal to 0, or the negative definite. And this is the block diagram of our sliding mode control of the proposed exoskeleton. Given desired force, sliding surface, from the dynamics of sliding surface, we could get the controller U that will actuate the exoskeleton actuator, and it has inbuilt position sensor, which is a potentiometer that will help us where we are standing. And the force sensor, which is through FSR sensor, we could get the force value that is fed back to have the F actual in terms of experimentation. And the experiment setup is shown here, again with the driver circuitry, which is interfaced between the control computer with the LabVIEW platform and the hardware exoskeleton through NI DACON. Our system components precisely are Actuonics linear actuator with this specs. The actuator comes with its own custom microcontroller, which is known as LAC board, and the force sensor, which is to have the budgetary components. We have purchased this FSR 402 sensor only, and we are always utilizing the NI USB DAC, and then LabVIEW real-time platform with the graphical user interface is basically providing the control, where we have made our custom control code through this platform. And we have performed this with 12 elderly subjects. Of course, they are not patients, but elderly, definitely we have found that they have grasping strengths comparatively lesser as compared to that of youngsters. And we have obtained the statistical terms like in such a way that what is the length and the length and also the weights of them, thickness as well as for the 2 digits of these 12 subjects. And then the age group of them is varying between 55 to 70, and the grasping task for them is to grasp small, medium, and large sized objects so that we could able to obtain a solution in such a way that that grasping with this controller, with this novelly developed exoskeleton, is providing successful grasping in spite of different sized objects and in spite of the different sized human finger lengths. And first we started with the step response, and we have compared that with the PID control. Obviously, sliding mode control will overperform the performance of PID controller. This is done with the given step force to grasp, and that is compared with both SMC as well as the PID controller. And the lambda is the control parameter that has been optimized in order to have the optimal sliding mode controller. So we have optimized through PSO technique the tuning parameter lambda. We did not give a trial and error based technique because it is going to be useful for the patients in the future. So in that time, we do not want them to put trial and error value and test it because it is quite a substance with 0 sense if we ask them to train by themselves or put the lambda value by themselves by trial and error. It is quite sense with no value at all. So that's why we have optimized that value and providing them so that the optimal value for this exoskeleton for this type of grasping task is 0.27 by PSO technique in order to have this controller working well. And this is obtained in such a way. How did you get this? That is the question here. This is done by minimizing the objective, which is nothing, or the cost function is the error between the desired trajectory as well as the actual trajectory. So of the force, given force. So that is getting minimized for an optimal lambda value. So that lambda value is coming out to be 0.27. That is selected for controller constant. And this is the step response that is obtained for the given 5 Newton for the thumb exoskeleton. And we have continued or taken the performance towards various tasks of having multi-step responses, like multi-step of force values are given, and that has been analyzed also. Okay, then we have taken to irregular sinusoidal response also, like we have given irregular sinusoidal force trajectories, and that has been also tracked perfectly or to some extent in a satisfactory mode by the index as well as the thumb exoskeletons. And then we have performed the repetitive analysis so that that could be done with the correlation coefficient as well as the root mean square error with both the index as well as thumb exoskeleton grasping task. And then we have done the force distribution analysis because our ultimate aim is that this exoskeleton having the placement on the human finger on the dorsal surface will help to have higher or larger normal force as compared to that of other forces. Obviously, we have obtained that also, that the force contour study or analysis shows that the red dot, which is having the higher value as compared to the lateral or other forces. So we could justify that this exoskeleton is meant to have larger normal force as compared to that of the other forces in while grasping different objects. And we have tested also with a disturbance with the step response based disturbance, like given here a constant value that response of 2 Newton is 2 Newton is given as external force. That is nothing but the that the reaction force, for example, you are making this exoskeleton is making the subject to grasp. For example, it is flexing the fingers. So what happens generally for the elderly or the stroke patients who lost the control of the hand for a long time, when we flex it, when we flex their fingers, they will try to extend the fingers in the opposite direction. So that is the task. For example, you are making the fingers of the stroke patients or the elderly patients to bend to grasp an object. So that time they provide that inertia, like the opposite direction extension. That is the spike coming out from the patient that we have tested, and that has been given as the external disturbance, and that has been solved robustifying way by this robust controller. And with this, I stop here, and by time bound that I could not add the video for that. So with this, I stop here, and Amit, I'm done with my presentation for today.
Can I ask a question, sir?
Yes, yeah, please.
Sir, how did you determine the grasping thing, sir? Thing is, but the actuator, no? So
Yes.
the different objects, the different sizes of the object.
Yes.
How did you come upon with when it should stop and when it
Yeah,
should?
actually, actually, this is the task. If you see that here with the controller block diagram, you can see, like for example, once the desired value of grasping, say 5 Newton is given, and the controller is in such a way that it will go reach it, make the XD reached. Okay, so that means your actual force is reaching the desired force. For example, it is given 5 Newton and I'm starting from 0 Newton. Okay, so when it reaches that desired value, it stops. It stops in the sense that it reaches there, but the holding force is still there. So that is the thing. Like for example, what I mean to say is the desired value is the one that makes the system to perform the task. That's all.
So there will be some patients who have muscle cramps and
Yes.
something like that. So they initially they will have some resistance pose when we are doing that. So even that, so those kind of patients, how do you
No. Actually, let me tell you very frankly. So far, we have tested only with elderly human subjects. That's all, with the age group of 55 to 70, who are nothing but our colleagues and our departmental staffs and faculty members only. Why? Because in order to test the system with the real patients who are having that type of tendency, like they cannot grasp and they cannot be able to obey this movement by the exoskeleton. So we have not tried yet, but of course that is the challenge really waiting for us. Why? Because why I say we did not do it, because we need to get the permission from the medical board of our nation, because implementing patients, especially patients for our research study, I need the permission, like our team needs the permission from the medical board of India, of our nation. So far we have not tested with the patients, rather we have tested only with the elderly human subjects. That's all. Did I answer your question properly?
Yes, sir. Yes, sir. Thank you very much, sir.
Thank you. Thank you, Dr. Sudhir. Yeah. And somebody typed some question. Can you please speak out? Somebody typed some question here in the chat box.
Sir, how we can manage the joint torque actually in 34 slide? Can you elaborate?
Yes, please. 34th slide. Yes, this one you are saying?
Sir, yes, sir, yes, sir.
Yeah,
The
actually
joint
what
torque.
happens here is, let me tell you very frankly, that for performing force control, you definitely need not only force control, even the position control also, you definitely need the dynamic model of it.
Okay, sir.
Okay, dynamic model of it. But you can see, I tell you very frankly, being a roboticist, I tell you very clearly, a very practical problem here is when we go something beyond the serial link manipulator. Say, for example, ours, like the previous exoskeleton and this exoskeleton are both a closed form solution, isn't it? Closed form based
Yes, sir.
expression.
Yes,
Like,
sir.
for
Agreed,
example,
sir.
it is not a serial link. It is having a 4-bar mechanism, which is a closed mechanism. And even this exoskeleton is also closed with the help of human finger links, finger phalanges. So with this type of closed chains, it is quite cumbersome. It's highly difficult to develop the dynamic model, because for it's possible for a regular parallelogram, it is easy for us to develop the dynamic model. Rather, if it is irregular, like the way which you have seen my this exoskeleton, if you see, yeah, if you see this type of irregular
Yes, sir.
4-bar based, it is highly impossible to develop the dynamic model. Whereas if it is a, if it is like, if this 4-bar, if this is basically a parallelogram, then it is quite symmetric, so it is possible to develop the dynamic model. Rather, if it is irregular like this type of shape, it is no way symmetric. It is, if this type of things are there, then it is quite cumbersome to develop the dynamic model. So for that, what is the concept, what is the idea we have taken forward is to use the this ideal dynamic model, like ideal dynamic technique, because the ideal dynamic technique is the one that has zero mass and unity viscous friction. So your highly coupled dynamic model becomes so simple equation like this. So
Sir, yes,
here,
sir.
here what happens here is your velocity becomes your joint torque. So you can
Joint
take it
torque, yes,
forward.
sir.
Yes. Whereas if it is a dynamic model, you all very well aware of the dynamic model, highly coupled dynamic equation it is. So it is non-linear equation. It is basically tau equal to b. B is nothing but the inertia matrix multiplied by joint acceleration plus Coriolis and centrifugal matrix. Say C multiplied by joint velocity plus G of Q plus friction. Okay, so these many terms are there. So to simplify that, I have gone with this idea. Why? Because this idea, how can you justify this idea? You may ask me, but I have read a book which is a very good book. It is by Bruno Siciliano. He is nothing but the father of robotics.
Type it in chat box, sir.
Yeah. Okay, fine. So
Okay.
let me find out. Where is the chat box first of all? Yeah, here it
That's
is.
why, sir, I'm asking you actually ideal dynamics and zero mass. That's why something in confusion in mind.
Yeah,
That's why
okay.
I'm asking you.
Yeah, okay, fine. So in chat box, what should I type now? It is basically ideal dynamics. Okay, ideal dynamics concept.
Yes, sir. Yes, sir. Got it.
Yeah. So Bruno Siciliano, I have typed there. Bruno Siciliano is nothing but a senior most faculty member in Naples, Italy. So he is nothing but the father of robotics. So currently, so from his book name is Modeling and Control of Robot Manipulators. So this is the book name. This is a Springer book, Springer Verla. So this book. So this book has a line about 2 lines, nearly 2 lines maximum. They said something about ideal dynamics in order to perform force control. So from that 2 lines, I have taken that concept forward, because you know that my robotic systems both are highly complex robotic systems. So
Yes, sir. Highly complex.
yeah, so what I did is, openly let me tell you, when I joined IIT Roorkee, I asked some of the BTech students to develop the dynamic model. So they could not make it. So I was not having time to do that, because when we do the faculty job, so We
Yeah,
don't
yeah,
get time much on our own research as well. So I utilized those boys, but they were also not able to do it. So rather, I found this idea of going into ideal dynamics. But let me tell you that nothing is impossible. So somebody can take forward, like coming out with a dynamic model and then performing like force control could be a better choice for their immediate research topic. That's all. And let me also put forward to all the general audiences that the new concept here is when you see that I have utilized the intelligent control technique for what type of work. It is a kinematic work, like kinematic control, isn't it? So the what is missing, what is the research gap nowadays with the intelligent control technique is basically intelligent control technique for force control is missing now. So when you take that idea towards the force control, you may be successful in getting publications also, because when you see the publications mostly with the intelligent control techniques, say neural networks, fuzzy, so those techniques involve only position control. Whereas when you take this step forward with the force control, then high chances for publications. That's all. So I think I could somehow answer you regarding this, how we could do theta dot. Is that okay, Dr.
yes.
Thank you,
Thank you,
Dr.
sir. Thank you, sir.
Thank you, Dr. Devraj. Yes, yes, I could see your message also. All right. So, any questions further, or Dr. Amit, Professor Amit? Yes, Dr. Shetan Ram, thank you very much. Yes. So if you have any questions, and let me quickly type my email ID here, and I'm open for your questions. So this is my email ID, m.orlando@e.iatr.ac.in. So thank you so much, Dr. Shetan Ram. Thank you very much. And if you have any questions, kindly do email me also. I'm glad to answer your questions. So the coordinators, can you conclude this session so that you can allow me to leave? Or thank you, Dr. Vinod, Dr. Saraswati. Thank you so much. And if you have any questions, you can ask now till Professor Amit can interfere us. Am I audible to the coordinators, course coordinators? Dr. Devraj, could you inform Dr. Amit about the conclusion of our session? Dr. Vaibhav. Thank you, Dr. Vaibhav. Actually, this session is basically a high-level session. For my knowledge, it is basically a high-level, workshop. It is basically people generally have robotics and automation, general robotic sessions only. But this is quite deeper. Like it has gone into the level of wearable robots. So something very good it is. So I appreciate the coordinators, Professor Amit, and other faculty members and the department head also. So if you could allow me, I can kindly leave the session by thanking you all. Dr. Amit, am I audible to you? Thank you, Dr. Olin Davids.
Yes, sir. Thank you.
Thank you. Thank you so much. And somebody from the Palaniyappan. So he has asked if I develop the new model and what methods I follow to measure the force. So first of all, to measure the force, first you need to go, we need to have the sensors first of all. So when you see the robotics field, I can very openly say that 50% people only will work in robotics. Rest 50% people are comfortable with the position control alone. So the moment you take force into your hand for work, for your research work, you are winning 50% in the straight ago. All right, so I kindly suggest you all take the force at your hand. So like take the force concepts, force tasks at your hand for research objectives. You are in the first go itself, you are winning 50% of the robotics globe. Okay, so that is my
Dr.
suggestion.
Flix.
Yes, Professor Amit. Yes, very good evening. Yes, please.
Actually, you were calling me and my audio was not working actually.
Oh, sorry. Yeah, actually, I want your permission to conclude here. So I am done with my talk
Okay.
here, and you can openly ask the
fine.
feedback even today now in front of me also. And if you allow me, we can conclude my session. Yes, Professor Amit.
I think you can conclude, sir, and then we can take questions from the participants.
Yes. So
after your
yeah,
conclusion.
it is done. Thank you so much, Professor Amit, and thank you, audience, for your cooperation. I have first time I have discussed this exoskeleton for grasping purpose because truly speaking, it is under review now in IEEE transaction journal. So still I have come forward because Professor Amit has very warmly welcomed me. Like he has invited me a couple of weeks ago. He has invited me very warmly, and also the workshop is quite informative and it is quite direct to my field. It is towards wearable robots. I think in India is the first time I'm hearing such a workshop towards such a narrow down robotics research topic. Thank you so much, audience, and thank you so much, professors. So any questions further in front of Professor Amit, you can ask. And I think all of you have noted down my email ID so that I can also be, I'm obliged to answer you all. Whatever questions pertaining to this field, you can ask me, I can email you. I feel that is my responsibility. Thank you, professors.
Dr. Flix, I think there is a question in chat box.
Yes.
Yeah.
That is that is what if I develop the new model and what method I follow to measure the force. First of all, one has to see whether it is, he's saying to measure the force, it means that one has to have the sensors. The simplest sensor is the FSR sensor to measure the force. And the model, what you can use is the dynamic model. If you develop a new model, that's what you are saying, no, Professor Amit from Palaniyappan, no?
Yes, sir.
Yes. So that's a new model. Definitely do not stay comfortable with only kinematics. So develop the kinematic model, develop the dynamic model, and then one has to have the force sensor in order to physically making the experimentation. All right, because definitely simulation study is not acceptable for paper publication. So paper acceptance demands experimentation. So you must have a force sensor, which is nothing but the FSR 402. FSR 402. So this sensor is good enough to get the continuous force value, FSR 402. So this is the sensor which could help us to have the force feedback, like force sensing part can be done. And of course, Techniques wise, if your system is quite complex, definitely start with ideal dynamics method, like which is nothing but the tau equal to theta dot. That's all. With that, you can go forward to utilize this type of block diagram, which is shown here, which is the technique is here. Okay, so this is the one. And then you can also have this. Let me get you one thing quickly. I will tell you the paper, which is nothing but a publication one. Let me put forward a paper which has the block diagram to have a simple force method approach using dynamics, like ideal dynamics. Let me find out now. Let me give the name of that paper. So okay, wait, let me do one thing. Here it is. This is the one I'm saying. Yes, so this is the simplest approach that you can use with the ideal dynamics. Could you see that the person who asked the question, Dr. Palaniappan, can see this slide. So this is the simplest approach that can be helpful in performing the simulation study, and then later on it can be converted with the force study, like experimentation with your force sensor. Yes, so he has. Yes, thank you, Dr. Palaniappan. So I have received your message also. Thank you so much. And any more questions from the audience? Professor Amit, you can help me.
Yeah. Dear audience, if you have any other questions, so it's a very right time to ask. Those people who are directly working on the hand rehabilitation may ask if you have any doubt. So meanwhile, can I ask a question, sir?
Yes, please.
Sir, actually, I am also interested in this field, but means I have seen your work, and it is really a wide opening session.
Thank you.
Which material may be best suitable to make the soft robotics?
Material is precisely
silicon or something else.
Yeah, silicon is the one that is highly good for soft robots. At the same time, since it is an exoskeleton meant for applying force on the object, we must also have the material to be strong enough. So there is a trade-off that it has to provide the normal force to the object, because it will make the finger to grasp an object. So it has to provide that sufficient force to the fingers. So in that way, what we have used is polycarbonate, which is nothing but the plastic material that is meant for us in our tinkering lab. Okay, so that is the polycarbonate material what we are using presently, and also there is some other which in IIT Kanpur also people are using, acrylic material.
Right, acrylic sheets and polycarbonate.
Yes. Polycarbonate is opaque material, whereas acrylic is transparent and it looks so what we need is also when we wear this hand exoskeleton or leg exoskeleton, we need somewhat aesthetically it must be good also, because we are wearing it. So acrylic is quite transparent and will not project that we are wearing something, because it's transparent. That's all. And also it is lightweight, and also it is providing good force to the fingers. That's all. So I suggest from my point of view, I can, from my experience, little experience, I can tell that acrylic and polycarbonate. These are the two materials that can be helpful for it.
Okay, sir. And what about dielectric?
No, currently I do not have any idea about it.
Okay,
So
okay.
I cannot say anything about that. Sorry.
Fine, because in the previous talk, there was a Dr. Deepak Kumar was there from MNIT Bhopal,
I see.
and he suggested that you also can go for dielectric,
I see. Okay. Fine.
but that may be a different material. So
Yeah. Okay.
I'm in the process of selecting the suitable material. So I usually
I see.
ask this question.
Okay. Let me give you the name of a faculty member.
Yes.
Okay, so he is the faculty member who can answer this question. The material one is well answered by this faculty member who is my guide during my PhD. So he's from IIT Kanpur, Professor Ashish Datta. So he's an expert in exoskeleton in India.
I know him, sir. Actually, he's very well-known person.
Yes. So
And,
he's the right person to
yeah.
answer because he's working deep into this field because he is doing FEM analysis, finite element analysis also, so to get the proper material. So that is it. So
Fine.
he may be the very great person to give the right answer. If you want, I can even very well ask him and email you also.
Okay, very well.
Yes.
So definitely, I will write again to you, sir, to seek some
Please.
help.
Thank you, Professor Amit.
Regarding material and some other things also.
Sure. Yes.
Audience, if you have any question. Sir, Dr. Felix,
Yes.
If we are using any material, means let's say polycarbonate or silicon or any other material, so is it dangerous to put the wire through it and supplying the voltage? Is it dangerous or is it okay?
It's okay. There is nothing wrong in it because the wire is going to be definitely insulated. Like you will be having an insulation around the wire, so it won't be a problem at all.
Okay. I asked this question because let's say we are making a project for paralyzed people. Means who has a hand, and we are making a solution along with the hand, so that natural hand should not be affected by the voltage, and so
I see. Okay.
So you said there is no harm, right?
Yeah, no harm at all, nothing to worry.
Okay.
And yes, and currently myself, Professor Ashish Datta, is basically the grant project coordinator. We are kickstarting a new project on rehabilitation robotics, the whole body exoskeleton. In that, I am starting a new project on leg exoskeleton, planning to develop a leg exoskeleton, which is basically passive system. Like, for example, active system is the one that uses actuators to move, whereas the passive system will not have the actuators at all. So we are planning to develop a leg exoskeleton for the elderly patients to sit and stand. So that is our goal for the upcoming project that is going to start from January 6th next year onwards.
Very fine.
Yeah.
Actually, I came through the Professor Ashish Datta profile, and he is really means a legend person, at least in our country, in rehabilitation.
Definitely, yes.
Yeah. Okay, so he was your guide, right?
Yeah. I had 3 guides during my PhD. My main guide is Professor Lakshmidhar Behera. You may be knowing any of you.
Yes, I heard about him.
Yeah. So and Professor Ashish Datta and Professor Anupam Saxena.
It's very great to hear from you, sir.
Thank you, Professor Amit.
Thank you. We will be in contact, definitely.
Definitely, yes, please.
Yeah. And in future, near future, we will again organize such kind of events.
Definitely, yes. True.
And then we will request you.
Yes, definitely. And if it is not a COVID situation, definitely I would have visited your institute also.
Right, sir.
That will be good. Thank you. Any more questions, professors?
So I think, sir, let's be here for 5 more minutes. So if
Yes.
any audience wants to ask,
Sure.
Professor Dr. Premnath is asking to update on the attendance and test timings. Okay, sir, attendance. This WebEx platform is automatically collecting the attendance, so there is no issue on that. And test is tomorrow from 2:30 to 4:30 session. It will be feedback and valedictory followed by the test. I will write it to all the people. I have sent the schedule also. It is likewise. But in this session, please be focus on the this rehabilitation hand, and we can get the advantage of Dr. Felix expertise.
Also, let me tell you that my major currently my major research area is towards the cancerous treatment by medical robotic systems. So I'm developing a percutaneous needling robotic system that is meant for minimal invasive surgery. So that is currently my major research area.
Okay.
So in the future, if I get a chance, maybe I will discuss about that also in the near future. If there is a chance for me to have a talk in the future.
Right.
Yes.
Right. Very right.
Thank you.
Sir, the session was really very informative.
Thank you, Professor.
Yeah, and you answered all the questions very nicely. And
Thank you.
means you, because you are doing research on means real hardware. So actually, it when we touch the hardware, we got a number of problems, and that is the real knowledge.
Thank you. Yeah. Because hardware. Because whatever projects I do, that is demanding the product output. That they need the project itself demands the product output. It's not merely publications, but the product must come because it is basically a medical device based project. So obviously we try for experimentation, and we want the Indian society to be benefited by our research. That's our ultimate goal. That is why instead of there are so many robotic domains, for example, humanoid robotic system, rescue robotic system, and entertainment robotics. In all these space robots, underwater robots, robotics field. With all these, I have chosen medical robotics because it is what we need our health to be the first and foremost priority in our life, isn't it? So in that way, our health must be benefited.
Very right, sir. Very right.
That is why the target is towards medical robotics.
Very right. Sir, when you develop the robotic arm especially,
Yes.
so which type of controller you prefer to use? Control system.
Control system wise, we need to go like it must be intelligent and it must be robust and it must target force application. These are the three things I focus. It must be an intelligent control because suppose we have a system like the one which I have where I do not have the dynamic model at all. I cannot able to develop. So that way, once I do not have the proper dynamic model, control becomes tedious. So intelligent controls motto is we have less information about the system. We have very less information about the system. So with that, we could able to control by the intelligent control technique first. Second is mere intelligent control is not sufficient. So we need to go for robust control because we need to take care of the disturbances that is coming out then and there. So to address them, we definitely need a robust control. Third point is we do not want merely position control. Like we do not want to reach there. We need to reach there and interact with the environment. So interaction control, that means force is coming into picture. So these are the three aspects: intelligent control, robust control, then force application. So the control technique which I feel like I am working on currently is intelligent robust control. Not only intelligent, intelligent plus robust mixed. It's a hybrid control. That's
Fine,
it.
fine,
Yes,
fine.
yes.
Yeah, I got some points what you are saying, because my colleague is an expert in fuzzy logic controller. I'm not the person from control system, so I understand less. He is trying to fit the fuzzy logic based controller involving reinforcement learning also.
I see. Good. Yes.
But what you have suggested, that the force and
Application, force
yeah,
application.
fine.
Because if you see the publications, Prasamit, if you
Yes,
see those publications with intelligent control, mostly 70, 80, 90% of the published papers stay only comfortably with the position tasks.
right.
Whereas force tasks are difficult. Why? Because most of us do not have force sensor, first point. And second point is how we correlate the motor actuation and the force value. How it is getting correlated. That correlation also people are hesitant. People are hesitant to go forward.
Yeah.
So that is the thing. So these are the important aspects that one has to have. For example, I'm trying to buy a force torque sensor, nano 17, nano hyphen 17 FT sensor, force torque sensor from one company. That the cost is very high. It is nearly 9 lakhs, but the budget allotted is only 4 lakhs. So I could not able to buy that. So these are the reasons that we are not having the proper equipments for force application. So we are not able to do that. So, in that way, we are lagging behind the 50% of the force sensors. We're not going beyond that. So one has to first of all pass these hurdles to to perform the force-based intelligent control techniques.
Yeah, completely agree, sir. Completely agree.
Thank you.
And one more question.
Yes.
Before Devraj Vishnu, sir, which type of motors do you use to rotate the fingers?
Yeah, I use. You can see here there are various motors which I have used. So if you see here, let me show here. Yeah, can you see this? This is basic. Can you see this slide?
Yes, sir.
Yeah, so these are nothing but the ultrasound, ultrasonic USR, ultrasonic motors. So this is providing high torque, but the problem with these motors, because why we need motors in such a way, this type of motors, because it is a direct drive. Okay, direct drive means on the finger joint, this motor is going to sit. So what is necessary is we need a small sized motor with high power, like high torque it must provide. So with that, we have purchased this. In 2011, we have purchased these motors. But what happens here is these connections between the wire and the motor is basically in such a way that if it is bent, no, then we are out. We cannot even solder it. We can solder, but by soldering, we will not get the proper working functioning of this motor back. So this is the main problem, but the cost is very high here. It is in Indian money. That time it was 10,000. Maybe by this time it will be doubled probably. And this is the problem with this motors. There is another motor, which is basically the commonly used stepper motors. These are these motors, which sorry, stepper. It is servo motors. These are the servo motors, DC servo motors. These are available less than 500 rupees. But the main problem here is these work in the basis of 1 degree steps. Like we get a smooth joint angle. Each joint angle value is varying very continuously. Like you cannot say that it is a discrete value. It is almost like a smooth value, like 0.1, 0.05. These are the discrepancies. These are the values increment of the joint angle. But 0.25, 0.18 degrees, you cannot give to this angle, this motor, because this motor takes a minimum value of 1 degree.
Got it, sir.
Yeah, 1
Getting
degree
it.
is the voltage corresponding to 1 degree is the minimum angle this can move. Whereas this precise ultrasonic, this motor has very good potentiality. It can move. But the problem associated with this is again the connection between these wires and the motor platform. So this, if it is bent by any moment, like that will also lead to problem. So
Yeah, got it. Up to some extent, I got it. Hello, Dr. Flix. If I am audible to you, we can take the last question because we are running out of time. The question is how the back EMF could be mitigated in such high torque drives. Professor Felix, if you are not audible, sir, if you are speaking. Maybe you can type in chat. Hello, Professor Felix. I think there is some issues Professor Felix is facing. Hello. Hello. Am I audible? Can anybody confirm?
Yes, sir. Yes, sir.
Yes,
Okay. Yeah, I think there is some audio disturbance from the side of Professor Felix, but it is really a good session, and I think our speakers were good. At least I enjoyed their session and learned a lot.
Yes, sir. Yes, sir. Definitely.
Yeah. And dear all the participants, soon we are going to organize another workshop, but it will be for PhD scholars. So if you are PhD scholar, then it may be beneficial for you. The topic will be same, wearable and rehabilitation, and it will be scheduled in June. And then obviously I have your email IDs. I will again inform you. But I think that that is from SERB and it is for PhD scholars, I think. Let me check all the eligibilities, and then we can once again come get together. And meanwhile, we may be in touch to know what each group is doing. Professor Felix's EF. Okay. Yeah. Anyways, I think Dr. Felix is disconnected, but the session was really good, and I will send him the regards on behalf of the audience. Okay, let's close here because the time is also over, and let's meet tomorrow. So let me tell you the tomorrow schedule because it is little bit different. We have our regular session from 9 to 11, again on soft mechanics or rehabilitation kind of topic. 9 to 11 is our regular session. Then 11 to 1:30, a different session, means yoga and mental peace, and we will enjoy that session. And then after lunch at 2:30 to 4:30, we will have a valedictory session, valedictory and feedback and test. So after giving you a thank you note and everything, I will send you the test. Test is objective type, and there will be a. I am preparing the test itself right now, and based on the number of questions, time will be allotted, and it will be written there. Question paper will be objective type, and if you have attended 80% sessions, because this is an eligibility criteria, and then you have to score at least 60% in the test, and I think then ATAL AICT will issue the certificate to you. All the best. See you tomorrow. Yeah, I will send you the link, the recording link to, I think, every participant. We will. In fact, I will again hear the interesting sessions of all this. Okay. Thank you very much, Baneji. Now, please stop the recording. Okay. Bye bye. See you tomorrow.